Today's lesson is going to be on synchronous counters. It's the first booklet of the upper sixth electronics course. So I'll give you a copy of this on Google Classroom. So chapter 1 is on further sequential logic systems or synchronous counters. I think the first thing to do really is just a little recap on counters that we did in the lower sixth. So I'd urge you to go back and read the booklet on that, just to recap that, because it does relate to these. I'll show you here what I mean. So looking back at the lower sixth, we did binary counters using here the D-type flip-flop. So we've got 3 D-type flip-flops. If I press play, you can see we've got a 5 Hertz pulse feeding into the first D-type flip-flop. The output here, Q, it goes to A here, and then not A here, goes back round to the input D. If you remember the D-type flip-flop, whatever data is present on the D input is transferred to Q only on the rising edge of the clock pulse. Okay, that has the effect here of halving. It's like a toggle latch, so it halves the frequency, so we have 2.5 Hertz here, and then the process is repeated again, and effectively each time it halves the frequency, and we get the output the same as a binary, in this case a 3-bit binary counter. If we want to add more bits, we can just add more D-type flip-flops and daisy chain them along. The reason why it's called a ripple counter is because the signal comes into this D-type flip-flop here, and then the output controls the input to the next one, and the signal ripples down a bit like dominoes when they fall down to the last counter here. Obviously, a 3-bit counter can only count up to 7. If we had an 8-bit counter with 8 D-type flip-flops, that could count up to 255, or even up to a 16-bit D-type. 16 D-type flip-flops would give you 65,536 different combinations. You can imagine once we get to a larger number of flip-flops, it's going to take a while for the signal to get from one end to the other, to ripple down to the end of the counter. Each D-type flip-flop might have a propagation delay, which is the time taken for the output to change when there's been a change in input. It could be something like 10 nanoseconds. So if you had 16 of these in a row, the overall time it would take for the signal to get from the beginning to the end of the chain would be 160 nanoseconds. And that limits the frequency that the counter can count at, because if you go faster than the time it takes for the signal to get from one end of the chain to another, then the counter will glitch and will count wrongly. So ripple counters are limited in the speed that they can count at. It depends on the propagation delay of each D-type flip-flop, and it depends on how many D-type flip-flops or how many bits the counter is. So although ripple counters work very well, they're limited. The other thing they can't do is they can only count up or count down. They can't count in any other sequence at all, and that's where we come to the synchronous counters here. So we're going to be looking at how you connect D-type flip-flops together to make a synchronous counter, something called state diagrams, and how we design and so on. So it's going to be the first lesson on this today. So going down here, a basic synchronous counter has particular advantages. They can produce any sequence of output signals, so they can produce different patterns of outputs, so they're known as sequence generators as well. That means they can control things like industrial processes, or even just do simple things like Christmas light shows and pretty patterns and things like that. They can count up and count down as well. The clock inputs, this is important, the clock inputs of all the stages of the counter are connected together, and so receive clock pulses at exactly the same time, which is why they're called synchronous, because they're synchronized together. That means they can count at a much higher speed, because the clocks here are all connected to the clock inputs of the D types, rather than going to that one, which then goes to that one, which then goes to that one, like in the ripple counter. So we don't have this problem here where they can basically count much faster than the ripple counters. So if we just connect it up without, you can see here the basic structure of a synchronous counter is similar to the ripple counter, but we don't just connect not Q back to D. Each counter isn't connected together apart from here with the clock pulses. And the whole kind of shtick they have is that you use logic systems connected to the data in of each flip-flop, and then the outputs A, B, and C that are already there are connected to these logic systems to make the count or the sequence go in the particular way that you want. Okay, so let's just have a little look at that on Circuit Wizard. If we flip to a blank synchronous counter, rather boring, you'll see this does absolutely nothing. I press play, click it on logic levels. You can see we've got a clock pulse here feeding into the clock. It does absolutely nothing. We need to add logic systems to these D inputs here to make it do anything. So really it's all about designing these logic systems. And generally we design a different logic system individually for each of these inputs. And that's really what we need to look at now. So let's do an example, is probably the best way towards doing this. So designing a synchronous counter, the first step is to formalize, meaning just write down in the table, the required sequence of output states. So we need either a table or something called a state diagram. We need to decide what sequence the counter needs to do. So in this case, we're just going to copy the ripple counter. We're just going to do, as an example, I'm not sure it's the best example in some ways because it is a little bit complicated to do, but you'll see really it's the process of going through. So if we were going to make a 3-bit up counter, just like I showed you with the ripple counter, how would we do that with a synchronous counter? So first of all, we need to decide on the sequence. And you can see here, we're counting up in binary 1, 2, 3, 4, 5, 6, 7, and then back to 0 again here, and so on. So the sequence needs to go around in a loop, going through every single possibility from 0 up to 1, 1, 1, and then back to 0 again. Now to do this, to work out the logic circuits, we now need to split the table into two. We have to do the current state, so here we've got 0, 0, 0. And we need to then put the next state here. And this kind of seems a bit pointless at first when you're doing it, but you'll see the importance in a minute. So that's 0, 0, 0 is going to 0, 0, 1. Now we need to get this, what was the next state is going to become the current state. So 0, 0, 1 goes under here, 0, 0, 1, and that goes to 0, 1, 0, 2. And we do the same again. We copy that under there. So 0, 1, 0. Goes to 0, 1, 1, which is 3, and then we copy that under there. 0, 1, 1 goes to 1, 0, 0, and copy that under there. And it makes this rather pointless task at the time, it seems, but you'll see eventually we get to 1, 1, 1, 1, which is 7 here, and 1, 1, 1 needs to go back to 0, 0, 0. So this describes the state. You can see we've got output A here, output B, output C, and then we've got the inputs on the D-type flip-flops, input DA, DB, and DC. So somehow we've got to generate correct logic for DA and DB and DC separately using the outputs A, B, and C. So I'll just move on from that. Hopefully it'll seem clear when we get to the end. I understand it's a little bit funny at first. So we need a logic system attached to DC of the first flip-flop, which uses the signals from A, B, and C to generate an output of logic 0. Here, that needs to be a 0, generated from here. That needs to be a 0, but that one needs to be a 1. And effectively, what we can do, if we look at DA, here we can do it visually in this case because DA is just the opposite of A. So we can where there's a 0, that's a 1. So we can make DA is just equal to not A. So sometimes you can just spot a pattern, and that's easy enough to do. Okay, DA and A are inversions of each other, so DA equals not A. So that's that one there. Moving on to DB, we've got a different pattern that isn't obvious here. It's not the opposite of B, so it's not quite as simple. So we use our old friend, the Carnot map. So we're going to fill in the Carnot map from this output here. So we're just looking at this in relation to these outputs. So we can fill in the Carnot map. Now, if you remember that we go bum, 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 and then filling it in off the table, we end up with 0, 1, 0, 1, 0, 0, 1, 1, 0, and at the bottom 0, 1, 1, 0 as well. And then we go 0, 1, 1, 0, filling them in. So if that fills in the Carnot map like that for DB, and we can take these two here are a group, and these two here are a group. So we can say that DB equals not B and A, or B and not A. And if you remember from the lower sixth, that expression here is exactly the same as B exclusive or A. Okay. Now, if you're not completely sure following this through, it's really just showing the process. We're filling in the Carnot map. We're producing the simplest Boolean expression that we can. The simpler it is, the better, because otherwise you'll end up with a really complicated circuit. So DB should be the exclusive OR of A and not B. And then finally, we've got an awkward one for DC. And I wouldn't necessarily expect you to be able to do this off the top of your heads, but this is, as I said, a little bit of a complicated example in some respects. But we fill in the table from DC here. We get that. And then that gives us one group, which is C and not B here. And then we've got these two awkward ones that are on their own. So we can give them their own expression. In this case, it's not C, B, A for that one, and C, B, and not A for that one. Now with some jiggery pokery here, doing a bit of Boolean algebra, we can effectively see here, we can take B from these two terms, we take B out of the equation, you end up with that. And that, again, like the one up here, is equivalent to C XOR A. So we end up with this rather horrible C and not B, or B and C XOR A. Yuck. Okay, moving on. What do we do with those now? We've now got three expressions, three logic systems, DA, DB, and DC. Well, we can actually connect them here. There's your DC here, and there's your DB, and there's your DA. I'm going to show you how that works on Circuit Wizard. Try it yourselves if you've got Circuit Wizard working. I'll click over to it now. So this is the 3-bit synchronous up counter. And I press play here. Should be able to see, I've got on logic levels, it's counting up in binary. 2, 7, 0, 1, 2, 3, 4, 5, 6, 7, 0. So we've got the table here, and it should be counting in. You see here, DA is equal to not A. So that's very similar. It's the same as the ripple counter. That is just connecting back round like that here. DB equals B and XOR A. So we've just got an XOR gate here connected to A, and the other input connected to B. There's that one there connected to B, and that one connected to A. And then DC, this one here, there you've got the OR gate and you've got the two AND gates here. We'll follow that round. That bit there matches that, and you can see it counts up from the clock input here, connected to each clock input. It basically does the same job as the ripple counter, but it takes a lot more work to make. The benefit of it is it can count a lot faster. But this is really just one example of what a synchronous counter can do, because you can make it do any pattern you want. So it's all about getting these logic circuits correct that you attach to the inputs of the D-type flip-flops, or the D inputs of the D-type flip-flops, and then the inputs of those logic gates go from the outputs A, B, and C. So I've given you a copy of this. You can have a play with that yourselves. Okay, right, back to this. A couple of important points. When a system is powered up and you switch it on, it could start in any of the states. However, in this system, no matter where it starts, then it will just get into the main sequence and count right through. So it wouldn't matter too much. You could put a reset on it to force it to start at 0 by connecting together the reset inputs, the D-type flip-flops, and connecting them to a switch or something, so you can reset it back to 0, 0, 0. As it says here, this system is a little unusual in that the required sequence, called the main sequence, includes all possible states. In many cases, some of the possible states are unused. You don't have to use every possible combination in the sequence. This can cause problems, as shown in the next example. So, example 2. This time we're going to design a LED light chaser. So it's going to start off blank, and then we're going to have an LED come on here, and then the next state that LED, and then in the next state that LED. So there's 4 states altogether that we're going to use. All of them off, that one on, and then that one on. And we can draw that in something called a state diagram. And this is just a diagrammatic way of showing the table. So we say state 0 here, 0, 0, 0. That goes to state 1, which is 0, 0, 1. That goes to state 2, which is 0, 1, 0. And that goes to state 3, which is 1, 0, 0. And then importantly, that goes back to the beginning again. This is what we call the main sequence, in that this is what the counter should be going around all the time. The problem is it doesn't use all the possible states that exist. If we've got a 3-bit counter system, then the possible number of states are 2 to the power 3, which is 8, including 0, 0, 0, up to 1, 1, 1. That's 8 possible states. And we're only using 4 of them, so there's 4 possibilities that aren't being used. And we have to take care of those, because if for any reason the system gets into one of those states when you switch it on, then you need to make sure it gets back into the main sequence. So the 4 unused states are 0, 1, 1, 1, 0, 1, 1, 1, 0, and 1, 1, 1. So we have to sort of make sure they're included in the sequence. So we complete the state diagram by showing how we'll deal with them. We could just make all the unused states go into 0, 0, 0. That would work, but it's often not the best way of doing it, because you can end up with a complicated logic system. So what we try and do is make the unused states go back into the main sequence whilst keeping the logic system that we're designing for the counter to be as simple as possible. So suppose that the system starts in an unused state and outputs 0, 1, 1 here, then it should find its way back into the main sequence and go around like that. So here's the truth table for this system. 0, 0, 0 goes to 0, 1, 0, 1, 0, 0, 1 goes to the main sequence, and we go back there. But this bit here up to there, 0, 0, 0, this is the main sequence in blue. After that, these are the unused states, and we're deciding where we're putting them. They're all going to 0, 0, 0. Okay. So if we then worked out the Boolean expressions using some Carnot maps, we don't need to use a Carnot map in this case, because we've only got 1, 1 in each one. So we can just do the Boolean for that. So DA is not A, not B, and not C. DB is going to be A, not B, not C. DC is going to be not A, B, not C. Okay, really fairly straightforward. So we're going to have to use 3 input AND gates to do this. One thing to point out, the D-type flip-flops have Q and not Q outputs, so we don't ever need to use NOT gates. We can just use, instead of C, we'd use the, on output C, we'd use the NOT Q output to get NOT C. So we never need to use the NOT gates. We can miss those out. I'll go around to here. That gives us a system that looks like this. DC, B, not A and C. You can follow these wires around. They either go to B here, not A there, look, goes around here, right around there, and there's not A. Not C is here. So they all connect together. You can try building that yourselves if you've got Circuit Wizard. If you haven't got it working, here's what I prepared earlier. Just like repeater. There we go. So here's the light chaser. If I press play, logic levels on, and you can see 0. It makes a little light chaser. You're thinking, now this is how Christmas lights work and things. And yeah, it is. Okay. So quite a complicated circuit to make a little light chaser, but it's not too bad really. You've just got 3 input NAND gates and 3 flip-flops. And that works quite well. Have a go at building that if you can. I'm going to include these as files. You just want to play around with them. So, okay, so we've got another thing to think about here. The drawback of connecting all the unused states to 0, 0, 0 state is that usually the solution leads to Boolean expressions and logic systems that are more complicated. It hasn't particularly made an excessively complicated one in this case, because there's only one possibility of when the output was a 1. So it was fairly straightforward if we use 3 input AND gates. The problem is, though, is if we don't take care of the unused states properly, we can have something called stuck states. And stuck states are unused states that do not progress into the main sequence. So if you had your logic circuit so it could produce the sequence, the main sequence going around like this, and then S6 and S7 feeding into S0, they're fine. But then if you had S4 and S5, if S5 gave the logic system made S5 101 go to 011, and then 011 went back to 101, you could just end up with a system where it's stuck between the 2 states and never get back onto the main sequence. This is kind of a lesson in why sometimes switching something off and on again works, because if you switch it off and on again, it may come back into the main sequence. What's happened is the logic system's got stuck over here. So we don't want them. They're a bad thing. So these are only a problem when you power up the circuit. But as you know, flip-flops can be a bit unpredictable when you power them up. So they could quite easily end up in one of these states and be stuck. So we have to take care to avoid these stuck states. Okay. Right, so what I want you to do, first of all, is just have a little go at this exercise 1.1. You can either print it off or just draw it in your books to take a photograph. It's very straightforward, very quick little task for you to do. We're giving you the state. I want you to fill in from the state diagram here. First you do the main sequence, then I need you to put the unused states in here and show where they lead to on the state diagram. Okay, so if you could have a go at that, that would be fantastic. That's me done. Thank you.